Massachusetts Space that we do is to bring in a distinguished individual once per year to talk about activities within various aspects of the space program. As you're able to see from the folder, we've had a very long and distinguished group of the previous 11 speakers in this series. Our speaker this afternoon didn't have to travel very far. Professor Claude Canizares has his office across the hall from this meeting room, where he is the director of the Center for Space Research. Claude received all of his education up the river at Harvard, has been a leader here at MIT in the development of what was earlier known as AXAF and now known as Chandra. Will be the subject of his lecture today. He has been notable for his government service and public service in helping all of us in having our space objectives realized. And among the many things that he has done, he's chaired the Space Studies Board of the National Research Council. It's my great privilege to introduce Claude Canizares to speak about probing the violet universe with the Chandra Xray Observatory. Right?
Thank you very much, Larry. Well, I guess I have to go on the air now. How does that work? Can you get some amplification back there? No. Did they get turned on? Maybe the amplifier isn't turned on. Well, while we're working on that, I'm more instrumented almost than the satellite you see in front of you, but the satellite's actually working well. No? You're on. Now I'm on. Oh yeah, so I turned the wrong switch. How's that? Excellent. Well, it's a great pleasure to be here and to have traveled so far for this occasion. It's also great because I always enjoy talking about this. I have been having an extraordinary amount of fun in the past year and a half since Chandra was launched. One of the things which I regretfully will not be able to do sufficiently is to mention the names of many of the people in this room and a great many more who are not in this room who contributed to the things I'm about to describe and made all this possible. One of the things that is a less described pleasure of working in an area like space science and space research is the chance to work closely with a great number of very dedicated and talented engineers, scientists, managers, people who bring together a lot of different skills in order to make a project like this happen. And so I want to start with a tribute to them, even though I won't have a chance to mention them all as we go along. Well, what just disappeared from the screen is the picture of Chandra. This is a large satellite that was launched by NASA just a year and a half ago in July of '99. And its purpose is to join with the Hubble Space Telescope, the Compton Gamma Ray Observatory, and shortly the Space Infrared Telescope facility in probing the universe with the greatest possible precision. This observatory, in contrast to the others that I mentioned, and the Hubble, which is probably well known to most of you, has been in the news a great deal, studies X-rays. In studying X-rays, we study the hottest and most violent objects in the universe. And so what I'm going to do today is to tell you a little bit about the satellite and some significant fraction of the scientific instrumentation was built, in fact, in this building and at MIT, and then another part up the street at the Smithsonian Astrophysical Observatory. And then to give you a little bit of a glimpse of the kinds of things that we've been learning with this remarkable new tool. First of all, a word about X-rays, since I know that many of you are very familiar, but some of you maybe not so familiar with the fundamental properties. X-rays are, of course, another kind of electromagnetic radiation, but with wavelengths about 1,000 times shorter, and therefore energies per photon or per quantum 1,000 times higher than that of visible light. And so having more energetic quanta, more energetic photons, means that in order to produce these X-rays, you have to go you have to have some object that's somehow either very hot or very energetic. So if you take the spectrum of radiation, of which visible light, of course, is only a very small piece in the middle, X-rays have a wavelength of about, in our case, say 10 angstroms or 1 nanometer, and correspond to a temperature of millions to hundreds of millions of degrees. And so that's the kinds of objects that we study. And of course, in order to learn about the universe, which is a vast place and which gives up its secrets only grudgingly, the goal in astronomy and astrophysics for the last 40 years has been to expand our grasp of this electromagnetic spectrum as much as possible, and an important part of that is this X-ray band that I will be talking about today. Now, I can give you a very close to home example of the difference between studying things with X-rays and visible light. This is our familiar sun, the photosphere of the sun. These days it's more active and has more spots on it, but otherwise it's a fairly bland surface. The visible light that we see is generated by gas at the temperature of the surface of the sun, which is the temperature of maybe 5,000 degrees, the typical temperature of a reasonable flame, and that's in a candle or a Bunsen burner, and that's why it looks the same color. If you take the exact same object and look at it with an X-ray telescope, as was done first about 20 years ago, and then more recently with a number of satellite instruments, you see a very different picture. This is the same sun, and those two pictures were not taken exactly the same time, but they could have been. And yet here what we see now is material not at the temperature of a candle flame of thousands of degrees, but at a temperature of millions to 10 million degrees. And this is very hot gas confined in magnetic loops in the so-called solar corona that extends way above the surface of the sun. And so when we look at the sun in X-rays, we see a very different set of phenomena. If we want to understand this very energetic phenomena, then we have to look with telescopes like Chandra. Now, why did I say that this picture and Chandra itself is a satellite? And why do we go to the difficulty, since the visible light picture was taken from the Earth, of putting our instruments in space? And of course, the reason is that the Earth's atmospheric mantle is extraordinarily opaque to X-rays, which is probably a good thing for us, but as human beings, but not such a good thing for us as X-ray astronomers. So, so the only way we can study these X-rays is to send our instruments above the atmosphere, and this was done first in about 1963 in a project led by the then MIT professor Bruno Rossi, who is in many consider the father or maybe the grandfather of X-ray astronomy. So we go up into space, and that's what we do in order to measure these X-rays. And the by far most precise and largest instrument that's been devised to do this is the Chandra Observatory. Now, the Chandra Observatory is an X-ray telescope. So it has something which acts like a lens, which focuses X-rays, which are shown here as little orange dots, focuses X-rays from a very distant source onto a sensitive detector at the other end, and which will then record the image. The key thing is that this telescope, which actually does the focusing. Now, focusing X-rays is an extraordinarily difficult thing to do, and that's one of the reasons why this mission was so long in the making. X-rays are very penetrating, and if you shine them straight into a mirror, they would simply absorb. And the only way to get X-rays to bend sufficiently to focus to a point, for example, if they come from a point source in the distance, is to coax them very gradually to change their direction by having them skip off a very highly polished surface, much as a rock you can skip off the surface of a pond, although if you threw it straight into the pond, it would just go plump in through the surface. And so Chandra has 4 sets of these highly polished, nearly cylindrical surfaces with very slight curvature to do the bending, and very highly polished in order to accomplish the focusing. And these mirrors were made over a period of many years at an outfit which is now Raytheon, but at the time was Hughes Danbury Optical Systems, and before that was Perkin-Elmer, and in which guise they made the Hubble mirror, so we had a lot of confidence that this would be done right. And you can see here this polishing. This was really the heart of getting Chandra to have its properties, which I'll mention in a moment. And just to give you an idea, in order to make these mirrors, because you can see you're coming in at such a shallow angle, you have to polish a great deal of glass in order to get a relatively small frontal projected area, collecting area to collect the X-rays. In fact, the effective frontal area of this telescope is about 1,000 square centimeters, and yet we had to polish something like 20 square meters in order to get those 1,000 square centimeters of projected effective area. The surface quality is extraordinary. The average roughness of the surface is 3 angstroms, which is which I like to always make an analogy that if you were to polish the surface of the Earth to that precision, then the equivalent bumpiness of the surface of the Earth, if we scaled these mirrors properties to the Earth's surface, would be a few millimeters. So it's an extraordinarily well done job, and they did it well, and it focused when we got it onto orbit. The mirrors are then coated with iridium, a heavy metal, in order to increase the efficiency for bending these X-rays at glancing angle. And when we're all done, the telescope was assembled. This was actually done by Eastman Kodak. Everything is done under very clean conditions. In the space business, it's known that terrorists make excellent workers, and you can see they're already dressed for the job. A precision alignment, and when we're all done, the image quality that was achieved with these mirrors is something like a half an arc second, which is a factor 10 better than had ever been achieved with an X-ray telescope in the past. Well, the mirror, of course, is just what happens, what focuses the X-rays. Then there's a long tube. The whole focal length of these mirrors is about 10 meters, so it's an extraordinarily large satellite. The telescope in this picture would go in the front, fits in here along with the spacecraft, and then in the back are the instruments that detect the X-rays. And I'll show you those in a moment. Here's the spacecraft portion. TRW was the prime contractor, and this was the final assembly was in Redondo Beach, California, in their plant there. And this is the thing that has the transmitters and the power systems and so forth. The telescope fits in the middle of this, and this is, and then the solar panels stick out either side to make the picture that I showed you in the opening slide. Whoops. Oh, a little too. At the focus, then we have several instruments that can record the images. This one I'm showing you here was one of the ones built here at MIT in collaboration with MIT Lincoln Lab. It's a CCD detector, for those of you who know what that means, the charge-coupled devices, optimized for use in the X-ray band. And there are two rows of them. I won't dwell on that. But these have been developed in something like a 20-year effort, a collaboration between George Ricker and Mark Bouts and the people at Lincoln Lab who have optimized these for use with the X-rays. And they are an extremely good detector. I'll say more about them as we go along. And then the other instrument that was built here in this, largely in this building, is one of these two funny arrays. This one actually is the one that came from the German-Dutch collaboration. The one built here at MIT is slightly out of view here. These are periodic nanostructures which can be placed behind the telescope, these are sort of hinged structures. The telescope in this picture is sitting looking down on the floor below. Can be put behind the telescope and to spread the X-rays out in a spectrum, and I'll show you an example of how that works. And that's a collaboration which I had with Mark Schattenberg and Hank Smith over in electrical engineering and computer science, and to adapt the techniques of large-scale integrated circuit fabrication to the needs for our project. Well, finally, all these pieces came together. It says why it took 15 years to deploy the X-ray telescope. I didn't tell you that I was selected as a principal investigator on Chandra in 1984. I dare say there's some people in this room that were barely alive at that stage. And it was, for a long time I called it Orwell's curse, because at that point we were supposed to launch Chandra in 1991, and then the launch slipped a year per year for the next 8 years. And then finally it stopped slipping. We did a lot of political work and redesign work along the way, and in fact developed even better instruments. But finally, all those pieces, all those players that I mentioned, under the direction of Marshall Space Flight Center, which was the center that directed this effort, came together, and we were ready to go. Here is the Chandra was loaded into the Shuttle bay. Shuttle was the launch vehicle. After a lot of discussion, it turned out that that was the launch vehicle of choice. And the size of the telescope here, wrapped in its insulating reflecting material, together with an extra rocket stage, because the shuttle leaves this in a very low orbit and we wanted to end up in a very high orbit, just fills the shuttle bay. I mean, that's not by accident, that was by design, and luckily there were no metric to English conversions that got in the way of that activity. This was the shuttle launch in July of '99, first one commanded by a woman commander, Eileen Collins, and included Cady Coleman, who is an MIT alumna and also an alumna of the University of Massachusetts. So if the space grant had been around at that time, she probably would have been supported by the space grant. And she's the one who actually pushed the button to get Chandra out of the shuttle bay. And so the astronauts were ready. In fact, they were ready 3 times. They loaded themselves in, and there were 2 scrubs. And then finally, on July 23rd of '99, the shuttle took off just after midnight. It was an extraordinarily impressive sight. If any of you have not seen a shuttle launch, particularly a night launch, and are in Florida at the time, I urge you to do it. It's really extraordinary. It took off. Our little periodic nanostructures were in there being shaken to pieces, but not to pieces, it turned out, luckily. And then very shortly afterwards, when Shuttle got on orbit, they started the sequence to deploy Chandra. First, it's on a hinged system in the back, so that this thing, which used to be lying in the shuttle bay, is now already elevated to the position at which it will be gently pushed off just by mechanical springs that were released. Cady Coleman issued the command, and Chandra was off. Here you can see the telescope, and here the so-called inertial upper stage, which is the rocket that was to take it to a final orbit. Shuttle backed away a discrete distance, and that rocket was fired. Then a series of burnings, and it got it up to its final orbit, which is a 64-hour orbit with an apogee of about 140,000 kilometers and a perigee of around 12 or 14,000 kilometers. Here's the crew, very happy that they got this bomb out of the shuttle bay, I think, and they got their work done very early in the mission. You can see that in zero G, every day's a bad hair day, but they were indeed very happy. And I have to say, it was a great pleasure working with these astronauts who were very dedicated to this task of getting Chandra. We're very excited about the scientific implications of the job that they were doing in space, and came and visited us a number of times beforehand, learned about the mission, came afterwards to see how it was doing, and And that was another part of the privilege of working in these space programs, is to work with people like this. Well, the operations, as soon as the shuttle bay doors were open, Chandra was controlled from the control center, which is just up the street. It's in a rented space in Draper Lab. This is the Operations Control Center. It's the only control center that can run Chandra. It's the first time NASA has allowed a major observatory of this class to be operated entirely by an outside entity, not under their direct control. The Smithsonian Astrophysical Observatory is the parent organization. MIT is also involved in the Chandra Science Center that helps run this activity. And the operations have been extraordinarily smooth. It's really, again, one of the remarkable things is how well this has worked. Although I was just informed earlier today that because of another major solar flare, the satellite has once again gone into a safe mode, which it tends to do to protect itself when that happens. But other than that, which are more acts of God than man-made, the operation has been very, very good. So that brings us then to what we've been doing for the last year and a half. Well, the first several months, of course, we're checking out all the instruments, calibrating everything, doing all the usual things one does, learning a little bit how to operate it most efficiently. The operation now is extremely efficient. Most of the actual available time for doing science is spent doing science, not doing other things, which isn't always the case with missions this complex. So now I'm going to shift gears and stop telling you about the thing itself, and rather the kinds of things that we're learning. And this will be just sort of a light overview of the kinds of objects that we study, the way we use this tool to probe the cosmic violence I talked about in the title. So I'll start actually with something which doesn't appear so violent, but is a place where instead of stars dying, which I'll talk about in a moment, stars are born. And this is actually a Hubble picture, and occasionally along the way I will show optical pictures as well as the X-ray pictures to help orient you. This is a well-known stellar nursery in the constellation Orion, near the dagger of Orion, which is about 2,000 light years away, and contains a lot of dust and gas and new stars that are forming, bright new stars that are forming, many of which are in this picture are embedded and can't be seen behind the dust, and gas that have condensed out of this dust and gas and that are forming even as we speak, and some of them have formed just within the last million years or so, which in the lifetime of a star is a very short time indeed. Our sun is about 5 billion years old, so that gives you a scale. The power of Chandra, I think, for me, is best indicated by a picture like this one. This is a picture now not in visible light, but in X-rays, taken with Chandra, of the central part of this Orion star-forming region. And it shows this sort of dark X pattern that you see is just the boundary between the 4 CCD chips, and you saw that in the picture of the detector that I showed you earlier. You can see, a whole collection of objects. There are about 1,000 stars that are seen here, shining in X-rays. The ones in the middle they're so congested in this picture that they seem to all form a single blob. In fact, that's just the limitations of the reproduction that I'm showing you. If you look at it more carefully, as we have in actually a different picture, which takes care of the overexposure, you can see many, many very bright objects in the middle. Those are indeed very massive stars. Many of these are relatively low-mass stars that we think, like our sun probably in its in the early years of its life, were unusually active in putting out X-rays of the kind that I showed you on the sun now, but were a much larger part of the energy output in those early days. There are also objects here which we think are just starting to, haven't even turned into fully formed stars yet that are also, for reasons that are not well understood, putting a remarkable amount of their energy into X-ray production. And so this is an area that's a very active study of how this so-called violence that happens in heating the material to very high temperatures in the corona coexists with the other formation processes that are going on in the source. Now, whoops. Well, I think they really like this picture. Whoops. Oh, now we went to sleep for a moment. Whoops. We'll get back to, there we are. All right. So much for stellar birth. Let's go to stellar death. That's always more fun. A lot of the things that we study have to do with the products of what happens not at the beginning of a star's life, but at its end. This shows a visible light picture of a piece of the sky in the constellation Cassiopeia, which has been known for many years to be the remnant of a supernova explosion, a star that ended its life in a cataclysmic explosion, which we think is not at all uncommon way for stars to die, and which was probably seen by the astronomer Flamsteed about 350 years ago and recorded visibly as a bright object in the sky. The thing that's interesting from the point of view of astrophysics is this little debris here is the remnant of the explosion. All the other dots are just normal stars. And this is a visible light picture again, remember. And so this is just a little wispy stuff, which is a small amount of debris which came out of the inside of the star. Now, one of the things, there are a number of reasons why these explosions are of interest, but one of the things that interests me a lot, and some of my colleagues, is the fact that these are the sources, these supernovae are the sources of all the chemical elements that are of interest to us other than hydrogen and helium. In the early universe, there was virtually nothing but hydrogen and helium, and all of the carbon, nitrogen, oxygen, silicon, sulfur, et cetera, had to come out of the interior of the nucleosynthetic furnaces inside a star, and then be ejected so that it could mix with other material to form things like planet Earth. Otherwise, those elements simply wouldn't be there. So one of the things we like to study is the material as it comes out of the supernova explosion, because that's a unique opportunity to see stuff just as the star has obligingly turned itself inside out to allow you to look inside and see the material there before it disperses so broadly in the galaxy that it's no longer visible. I should say that this object is about 6,000 light years away, and it's about 10 light years across. That gives you a scale. That's this ring. Now, it turns out these things are absolutely ideal objects for study in the X-ray. Here's the Chandra image of exactly that same ring, that same piece of the sky. And now, instead of seeing a few wisps, it still looks wispy, but I can tell you that by adding up all the material here, we can see the bulk of this material that came out of the star in the center when it exploded is seen in this picture, now heated up to temperatures of about 10 million degrees by the shock that it encounters as it flies out from the initial explosion. And the initial explosion sends out the material at velocities of about 5,000 kilometers per second. So it's moving, and when it runs into stuff around it, it gets heated to these very high temperatures. Now, one of the things that is of great interest, as I just said, was to study the chemical composition of this. And the cameras that were built for Chandra give us really the opportunity to do that. The X-rays that come out have energies which are very characteristic of the element that's emitting the X-ray, so that you can actually do a chemical analysis by looking at the wavelength, the precise wavelength of the X-ray, or as it's depicted in this picture, the color. And I should say that the previous slide, the color was just used to indicate the intensity. Here is one case where the color is used to actually indicate the energy of the X-ray. And I can tell you, for example, that these red blobs over here are almost pure iron that was ejected from the interior of the supernova and that are flying out. And then there are others that are heavily enriched with silicon and sulfur. So we're actually seeing the elements that were synthesized in the interior of the star and are now being ejected, and one can do an analysis of those. And these are, I should say that this was a very massive star. It was probably about 20 times the mass of the sun before it exploded. So there's a lot of material there, and I'll be talking about, say another word about those kinds of stars in the next picture. Whoops, did I skip over? No, I guess I didn't. This is another case of such a supernova remnant. Here it is, this ring. Now this one actually looks smaller in this picture, and it appears smaller on the sky, but it's actually larger in linear dimensions because it's much further away. This is, but it's similarly the ring that's left over. This is again another Chandra picture. I'll tell you about this rainbow in a moment. Just look at this part for a second. This is again a picture of this stellar debris that is flying out from an explosion thought now to be about 1,000 years in the past instead of 350 as I showed you before. But again is the supernova of a very massive star. This is just much farther away. This is about 150,000 light years away in actually a very small neighbor galaxy of ours called the Small Magellanic Cloud. Now, I mentioned the other instrument that was built here at MIT is these little devices that, when put in the beam, spread the X-rays out in all their colors. And in this display, where we've also used the color of the display to emphasize that point, you can see little images of the supernova remnant, but displaced, and exactly where they fall depends on the wavelength of the X-ray that's doing the that's dominating the emission. And you can see from the labels up above that each one of those rings corresponds to a different element. So with this instrument, we can go along and actually measure independently the location in this supernova remnant of neon or magnesium or oxygen, and really do not just a chemical analysis, but a detailed spatial analysis of the material. And that, for example, gives us a picture of only, in this case, only oxygen, where oxygen was emitted in this explosion. I said this was a fairly massive star. This may have even been more massive than the previous one, but say 20 or so solar masses of star. It managed to turn itself into probably somewhere between 3 and 5 solar masses of oxygen alone. And it is these stars, which are relatively rare in the galaxy, but which, when they explode, provide the bulk of the oxygen that enriches the universe. And so they're of particular interest to those of us who think oxygen is a useful thing. And so when you take your next breath, you'll be breathing actually the piece of a supernova remnant. Luckily, it's cooled down by now. But and to give you a scale, our solar system has only a tiny fraction of a solar mass worth of oxygen. There's enough oxygen coming out in this explosion to seed, once it's finally mixed with other elements, many thousands worth of solar systems with the same amount of oxygen that we have in ours. So they're real stellar warehouses, if you like, of oxygen. One of the other things that we can do with this very fine spectral information is to actually look for velocity information as well, using the well-known Doppler shift, which shifts very slightly the wavelengths of the lines. And so this picture shows that remnant, and the arrows on top of it are to indicate the velocities that we can measure around this ring. The red ones indicate velocities away from us, so-called redshift, and these would be blue shifts, velocities towards us. And the scale is such that this arrow corresponds to a velocity of about 2,000 kilometers per second. So now we not only see the elements that are coming out, but we can actually measure the velocity of ejection from the original explosion and measure its energy. The total amount of energy that's released, by the way, in one of these supernova explosions is very considerable. It's 10 to the 51 ergs, for those of you who are working CGS units, the way we do, which is comparable to the amount of energy that the sun puts out on a daily basis, but if you add up that total over almost the full lifetime of the sun. So it's a very large amount of energy that gets put out. And that's what we're trying to measure. Now, those of you who saw this picture earlier probably noticed something which I neglected to mention, that little dot in the middle. And one of the other interesting aspects, in fact, this was actually our so-called first light picture. This is the first astronomical object that we pointed Chandra at. And as soon as it came up on the screen, all the astronomers in the room, focused on this thing, because this hadn't been seen before. It's because the previous images simply didn't, were too blurry. They were blurrier than this. And this just looked like another blurry thing, like that little blurry blob or that blurry blob. But when you have a very sharp focus, it turns out that that's effectively a point. For years, people had been wondering about what happens in this particular case, what happened to the very central part of the star that exploded to give rise to this debris. It's been known, again, for many years that these supernova explosions are not only the origin of the chemical elements in the universe, but also the origin of very collapsed central objects, the central core of the star, which collapses gravitationally and is what actually drives the explosion of the outer part, and which are either neutron stars or the ultimate collapsed object, black holes. And it was a puzzle why this object didn't have one, and the answer is simply it does have one, but it wasn't clearly seen before. So one of the interesting objects of study in X-ray astronomy is now I'm switching from the study of the debris to the question about the nature and properties of these highly collapsed objects, neutron stars or black holes. Neutron stars are stars with a mass comparable to that of the sun, but the dimensions of the city limits of Boston. So it's extraordinarily dense. They have densities of the nucleus of an atom, which I actually set on my calculator to convert, is about 100 million tons per cubic centimeter. And because of their great density, they often have very energetic phenomena associated with them, either because material is falling into them, because they're spinning rapidly. Their great mass density often translates into a great other energetic phenomena, and so they are very interesting objects for the study of X-rays. And I've got so many instruments here, I can't keep track of them. Sometimes these collapsed objects, either neutron stars or black holes, are formed in a supernova explosion in which the star that gave rise to that has a companion. And the companion could be a relatively normal star. By the way, I said that Chandra has very good angular resolution, but it wasn't good enough to take this picture. This is an artist's conception. This is a normal star, and it also doesn't show the X-rays as these funny little wiggly lines. But in which the companion is one of these very collapsed stars. It's so collapsed that as material is pulled off this companion star and falls down and down and down and down, seemingly forever, until it hits or disappears into the black hole. At the center, there's an enormous amount of energy released, more than you would get from nuclear fusion. For example, you could just fuse all that stuff in a reactor. So there's a great deal of energy emitted, and that energy comes out primarily as X-rays. And so these are objects of which there's a lot of interest, in which we can learn a lot, both about the objects and about how they interact with their companions by looking in Chandra. Here's just a picture of one of these in our galaxy, and you can see some of the streaks here from the spectrum that because this picture was taken with the spectrometers in place. But, and there's a lot to be learned, but more than I can tell you in this short time. So instead, I'm going to move to a larger scale. where you'll see these same kinds of objects, but now in greater numbers and from a greater distance. This is an entire galaxy of stars. And this one is a particularly active galaxy. It's a galaxy that's now outside of our Milky Way, which of course is our own galaxy, at a distance of about 10 million light years. This is a visible light picture, so you see in a lot of stars. These bright stars are in our galaxy. We're looking through, of course, the stars in our galaxy to see the more distant one. And this looks a little funny. It's disturbed. It's also, well, there are limitations of the PowerPoint resolution as well here, too. But you can see these dust lanes. This is an area in which there's a great deal of stellar birth and stellar death going on simultaneously. It's a burst of activity. When you look at it with Chandra, you see sort of an ensemble of things that are the same kinds of things I've just been describing, but now seen all together. There's a lot of diffuse gas, this stuff blown out here, and this is because there's so much stellar birth and stellar death going on here that that many supernovae went off more or less all at the same time and have blown out the whole inner part of the gas in this galaxy. And then you see these very bright objects, which are in fact X-ray binaries of the kind I just described, in which there's a collapsed remnant of a supernova that is accreting material and glowing very brightly in X-rays. This is our neighbor galaxy Andromeda, which is a little bit closer. It's a couple of million light years away, this is again a visible light image, and you see all the stars. A galaxy like this, and like our Milky Way, has maybe something like 100 billion stars in it. And the very center was imaged by Chandra. This little dark box here indicates the part in the picture I'm about to show you. And there again, we see these evidence for both some diffuse gas, but also these very bright X-ray binaries of the kind that I've been describing. But the center of this galaxy, and in fact we believe the centers of every galaxy, has another kind of object as well, and shown here as a blue dot because it has a different X-ray color. And these objects, we think, are in contrast to the sort of stellar-sized objects I've been talking about so far, are very massive black holes which are formed from the accumulation of debris from all the stars over the lifetime of the galaxy, collecting down in the very center of the galaxy, the lowest point, if you like, in the gravitational potential, where this debris collects and eventually collapses to form a very massive black hole. In this case, in the case of our neighbor Andromeda, something maybe around 100 million times the mass of the Sun, but in other cases up to a billion or even 10 billion times the mass of the Sun. Now these objects themselves are really fascinating in their own right. They are the largest black holes that we know about, as I say, up to 10 billion solar masses. And they cause a remarkable amount of disruption in their neighborhoods. The force of gravity is so strong here that material, as it falls in, again releases a great deal of energy. Processes that we don't entirely understand, but which I'll show you in a moment, conspire that as the stuff spirals in, some of it is actually squirted out again in extremely energetic jets where the material is traveling very, very close to the speed of light. So these objects are maybe, in terms of single objects, among the densest, most energetic in the universe, and of course, therefore, are prime objects for study with Chandra. Here's the center of our own galaxy, by the way, and this work is also being done here at MIT. This is an image of the center of our galaxy, and it looks kind of like that stellar birth-death case I was describing before. This is a region that's maybe several tens of light years across in the center of our galaxy. There's a fair amount of activity going on, not nearly as much as in the active galaxy I showed you before, but all these dots are probably X-ray binaries, and the general diffuse gas that you see here is mainly left over from supernova explosions. And there's one dot there, which is the massive black hole that's in the center of our own galaxy, which is actually remarkably quiet as an X-ray source compared to some of the others that we know, but is a very interesting one because, you know, it's our own and we feel a certain ownership of it, right? And, here's a case where we can actually see some of this energetic activity. This is another kind of disturbed galaxy. This is a galaxy which, again, has been known for some time to have a lot of activity associated with it. The dust lane, this is a visible light picture again. The dust lane indicates that probably there was maybe a smaller galaxy was swallowed up, fell into the large one and was stripped of its dust, and that may have triggered some of the activity. This galaxy is about 10 million light years away, and this picture is probably about from here to here might be tens of thousands of light years or so. Now, when we look at it with Chandra at this same picture, and it's roughly the same scale, this is what we see. Well, you can see the scale because actually this is a superposition. This is the optical picture seen in sort of bluish white light with the dust lane, and the red is the Chandra picture. And you can see sort of shining through without any doubt is a very strong X-ray source right in the center. That is the massive black hole that sits at the center of this galaxy. And you can see this long squirt of material coming out. This is one of those ejections, jets as they're called, of very energetic particles. And the fact that they glow in X-rays even tens of thousands of light years away from the center, and that it's so well collimated in a squirt is one of the things that we're trying to understand. What are the energetic processes that actually transport this large amount of energy so efficiently out such large distances from the central object? And then what can we learn, of course, about the central black hole in the middle? Now, when these things are farther away, these are more locally, this is actually, I say, is very energetic, but this is relatively puny to the most energetic of these objects, which are called quasars, which is cases where this same activity is going on, presumably in the center of a galaxy, but now at much greater distances and much larger energies. But before I get to the quasars, I'm going to talk about yet another kind of phenomenon where Chandra has helped us understand what's going on. This is an optical picture, actually, from Hubble of a cluster of galaxies. So far, I've been talking about individual galaxies with their 100 billion stars. Now I'm talking about whole clusters of thousands of such galaxies. And this is an example of one. These are found scattered throughout the universe. They are the largest gravitationally bound objects in the universe, in which thousands of these galaxies are close enough to swarm around and form a gravitationally bound system. Typical dimensions go up to millions of light years, a few million light years. In this case, probably this is only the very central portion, maybe only a few 100,000 light years across. Now, what we see here are all the visible stars in the individual galaxies. The hard dots, by the way, there are a few foreground stars that always creep into a picture like this, but most of anything that's fuzzy is a distant galaxy that's part of this cluster. When we look at such a cluster of galaxies with the X-rays, we see a very different picture again. Now, instead of the individual galaxies, for the most part, what we see is a glow of a very diffuse region of hot gas that's spread throughout the space in between these galaxies, and which actually contains more matter than all the stars in all the galaxies in the first place. Now, one of the things that I'll give you just one example of one of the things we're learning. This is a poor picture of another cluster of galaxies. I showed the one because it's much more dramatic. But you can see a couple of galaxies here and then a lot of other fuzzy dots. So this is a poor reproduction. But the reason that this is interesting, one of the things that we're just now revealing with Chandra, is that these things, although they're gravitationally bound, are still in the process of forming. And in this case, for example, I'm about to show you the Chandra picture. These are actually two smaller clusters that have just collided and started passing through each other. And we can see that in the next picture, where I'll show you what reveals that. This is basically the same piece of the sky, but now seen with an X-ray telescope. You see a diffuse glow from this very this very thin hot gas that spreads between all the galaxies in the cluster. And these rather sharp edges, we can actually measure the temperature and the pressure jump across the edges. These rather sharp edges are indicative of the fact that and this elongation is indicative of the fact that they're really two blobs of gas that have just finished merging and are one cooler than the other, passing through each other. So the dynamics of how these galaxy clusters formed is suddenly revealing itself in the by means of these X-ray pictures. Now the last thing I'll talk about is pushing to the edge of the universe, which is always, a good thing to do, particularly if you want to get headlines. And it's also a good thing to do because it really helps us understand the sort of evolution of processes in the universe from the earliest times to the present, and how the current universe that we live in and see around us locally came to be from the Big Bang itself. This is a Hubble picture, well-known Hubble picture. It's on the wall over here to the left in case you want to look at it more carefully later. A beautiful picture that was done by pointing Hubble at one point of the sky and exposing the detectors on Hubble for about a week. It was an odd piece of the sky where there was nothing particularly bright or interesting going on. And what it revealed, almost as if, when you look at a little drop of water under a microscope, is a teeming life of galaxies, all of which, at all distances out to the most distant galaxies that can be detected by present means. Chandra did the same thing. Chandra's field of view is actually a lot bigger, so its picture is much, much bigger. But in this exact same piece of sky, Chandra also looked for roughly a week, and to try to find out what was there. And these results are only just now coming out. This was given to me by our colleagues at Penn State. Here's a picture of just that piece of the sky, the Chandra image. And now you can see only certain ones of these objects are hot enough or energetic enough to glow brightly in X-rays. Each one of these is something different. Some of them have already been identified as supermassive black holes of the kind I've just been talking about, quasars that lurk in the hearts of massive galaxies. Others appear to be relatively normal galaxies that we wouldn't have thought have some kind of energetic phenomena at the center, but when you look with X-rays, you find that they are. And this is something which is just now people are starting to be able to do, to push to the largest distances, the highest energies, and figure out what in this variety of objects that you see in a visible picture can tell us about the energetic processes in the universe that we see in X-rays. Well, Chandra is itself, whoops, went too far. Why does it keep doing that? Chandra is itself an astronomical object. This is a picture taken by an amateur astronomer in Alabama shortly after the Chandra launch. And you can see this little streak here is Chandra moving across the sky during the time it took for him to expose this picture. I don't remember how long that was. It's in a very high orbit, as I indicated, which will last at least 50 years, if anybody's done the calculation of perturbations on the orbit. The design life of Chandra is 5 years, but we have no reason to believe it shouldn't last at least 10, and NASA has obligingly put in enough funding for us to operate it for 10 years at least. We have every reason to believe it's going to continue to be as functioning as well, because the engineers here and elsewhere did such a good job building it, and returning as many exciting results as we've just had a chance to glimpse so far. In fact, I have a feeling right now myself of having kind of walked into a banquet with a huge smorgasbord table, and I've just gotten through the first few appetizers, and although I feel like I'm already full, I just can't wait to get on to the main course. the results from this mission are really, I think, going to change a lot of what we know and think we know about the universe. There will be more surprises to come. The one surprise that I used to tell people before launch, that one thing that would surprise me most would be if Chandra didn't give us any surprises. And I think already from what we can see, I'm not going to be disappointed. Thank you very much. I'm happy to take some questions. Tom, could you flip the switch? Thanks.
Questions for Claude and the entire universe that is open as subject matter.
Pete.
What are the exposure times for a large scale photograph like that or image?
Exposure times, what are the exposure times for these images? They range. For probably the shortest would be about 20 minutes. And the longest ones so far are a week to 10 days. For those we can't do too many of, obviously. More typically, they may go for hours. Would be sort of probably the median observation. These X-rays arrive very slowly. The typical for a lot of sources that we're detecting, the rate of the actual photon arrival is fractions of photons per second. So, a photon every 10 seconds would be, a pretty good deal in our business.
The jet you showed coming out of the black hole was in one direction.
Yes.
Is that related to the angular momentum or something, or do they come in both directions sometimes?
It's thought that usually they come in both directions, and that one, the study of the counterjet, if there is one, has been kind of interesting. It looks like there is something going in the other direction. Some of that could well be a selection based on so-called Doppler boosting. I mean, if you're seeing you get an enhanced, the relativistic effect is such that you get an enhanced emission along the direction. And a lot of the jets that are seen in this business, all of which were first detected in the radio part of the spectrum, where you're looking at the synchrotron radiation of these electrons. And you're probably seeing just the ones that are boosted because they're beamed in a forward direction. It's probably a beaming effect for the most part, but there may be some where for some reason it really is lopsided.
Are these events related to cosmic rays formation?
Are these related to cosmic rays? They may be. I mean, it's thought right now that most of the cosmic rays that we see are probably come from things like supernova explosions, although now people are talking about very energetic cosmic rays may come from gamma ray bursts or something like that. Whether active galaxies generate a significant number of cosmic rays, I'm not sure. There are probably some who hold that they do, but I don't know that there's any firm evidence of that fact yet. Tony?
Are we able to detect emissions from really heavy elements?
Can we detect emissions from really heavy elements? We actually, first of all, it turns out that mainly what we're seeing are the most cosmically abundant elements. As I say, the signals are fairly weak. And so we see things up to iron, maybe some indication of nickel. Heavier elements are produced presumably in the explosion themselves. They're products of they're synthesized during the supernova explosions. And they may be there, but they probably are there in such small numbers that we wouldn't have expected to see them yet. And then you also have to find ones that have characteristic lines right in our part of the spectrum. So my guess is that we're not going to be able to say too much about the heaviest elements. There is a mission going up soon, a European mission called Integral, which actually should have the ability to detect higher energy gamma ray lines from heavier elements, maybe closer in on our galaxy at least, but then it would see some of the heavier elements.
If I might ask another question, what about the state of ionization typically?
I didn't mention that, but the question is, what about the state of ionization? We're seeing these elements, say nitrogen through iron, in very high states of ionization. Other than iron, most of what we're seeing are in the either hydrogen-like or helium-like state. In other words, it's oxygen with all but one or all but two electrons stripped off. Iron we see in a variety of states, but typically we have at least 10 electrons have already been stripped off. At these temperatures, that's the equilibrium value for those ions.
Numbers on your slide were the state of ionization.
That's correct. And in the astronomer's notation, in which oxygen 8 means oxygen plus 7 to a physicist.
You indicated at least one example at the end and others earlier where Chandra had followed observations that Hubble had taken in the visible with a good synergy between them. Have we started to see examples in the other direction yet, or is it too early?
No, we have. I mean, people have proposed to do Hubble observations to make sense of their Chandra observations. And in fact, right now, in an extraordinarily cooperative move between the two observatories, they're actually, when you propose, it's possible to send in one proposal to do simultaneous or contemporaneous Chandra and Hubble observations. So there is a desire to make the most of these observatories in those cases where that's a useful thing to do.
Well, you mentioned that there's more mass in the dust and the clusters than in the galaxies themselves, if I understood correctly.
Yes.
Could the missing part of the universe be that form, or is this in a plasma state?
Yeah. So the question is, could this gas in clusters be something about the missing? What is relation to the missing mass in the universe? It is in a plasma state. It's a hot plasma at typically 30 to 100 million degrees. And it's enriched with heavy elements, not as much as in the sun, about a third as much as what we see in the solar system or in the galaxy. But it is not anywhere near enough to provide the so-called missing mass in the universe. In fact, it is very useful because since these are the largest gravitationally bound objects in the universe, they probably have a mix of normal matter, baryons, dark matter, that's similar to the average in the universe as a whole. And all the models seem to indicate, and theories seem to indicate that that's the case. And so what we see is that all the normal matter, including the X-ray gas, which is typically 3 times what you see in the stars, 3 or more times what you see in the stars. So almost all the normal matter is in X-ray plasma. And then there's the dark matter, because the gravity that you deduce from the motions of this, in fact, just to confine the hot gas itself, requires another almost 10 times more material. And so that's where this statement comes that there still has to be dark matter. So in fact, studying that X-ray gas is probably the best way to really deduce how much dark matter there has to be.
In closing, let me offer you the certificate of appreciation on the basis
thank you.
of Massachusetts Space Grant Consortium, and the thanks to not only to you but to all of your colleagues who made this possible. It's extraordinary.
Thank you very much.